In the previous design attempt, we learned about how a hierarchical non-OO solution would badly violate the single choice principle because we actually transmit the data of the current state value at every level, especially for every subroutine that we're trying to use as helper routine. So now we would like to improve it. Conceptually, what you're doing is we want to move all the routines like execute, display, read, correct, message, and process into a single data, i.e. a single module or a class in the OO context. So in the previous design, we assumed that you have no access to a OO language like IFO, Java, or C# or even Python. But now, in the current video, we assume that you really do have access to a OO language. In that case, we can actually program an elegant solution to solving the interactive system problem. That's something we'll talk about this video from the supplier's point of view. And then in the next video, we'll see how you can use this particular pattern. To begin with, I would like to highlight the fundamental difference between a non-OO solution versus an OO solution. To see syntactically, you can already see the difference about calling the critical routine. So let's talk about the non-OO solution that we are already familiar with. Let's say over here. So we talk about the top-down design where we simply pass around the current state value from level 3 to level 2 and also from level 2 to every helper routine to level 1. So that's something we have seen already. So now let's see how we use the current states. So first of all, you can see the type of the current state is simply just a simple integer. That's why we had to pass around the data over here. And then how do we execute the states? Over here, execute. So we'll say execute states, and then you will simply pass the current state as a value so that display can also take the current states, read can take it, the correct validation can take it, message can take it, and also process can take it as well, right? So that's what we spoke about in the previous video, and we realized it really violates the single choice principle. So this is not a very perfect design if you have a choice to OO. Okay, so let's see fundamentally how can an OO solution prevent from violating the single choice principle. So now let's see this. Over here, let's talk about in the OO solution, the way you declare the current state would be like this. So now the type of the current states is no longer just a simple value integer. You can think about this is just a class. You can think about the class is basically an abstraction of all the state-related routines and data. Okay, basically all the states related routines and data. So everything that's related to the states will be put into this particular state class, as we'll see. So think about display, read, correct, message, and process. All these routines will be put into the class for states. And this is the law of inversion that we spoke about in the previous part of the lecture. So now once you have done that, what would be the beauty of this OO solution? Once you get a current states of type states, so now whenever you say current state.execute, so now execute, you can see number one, it does not take any parameter. Okay, it's simply parameterized, parameterless. Given that it does not take any input arguments, in that case, how do we know if the execute over here is really going to do the, for example, let's say if it is really going to do the display with respect to state number 1 or with respect to state number 2? How do we know? Okay, so now the answer is basically what we reviewed previously. It's really about polymorphism and also dynamic binding. Polymorphism and also dynamic binding. If you recall the essence for dynamic binding, which version of the execute it is going to call depends on the dynamic type of the current states. So the current state may be a descending class of the state class. So imagining that we're going to have a hierarchy for the state class. That's something we'll see when we present its architecture. Okay, dynamic binding. Okay, it's a very quick preview of what we're going to say for the rest of this lecture, this part of the lecture. Okay, so now what you really want to gain from this particular slide over here is think about this is what you have to do. when you only get procedural programming language available to you, in which case you have to pass around the current states. On the other hand, if you're programming in OO language, in that case, you don't need it. You can simply use the context objects and let the context objects dynamic type to decide which version of the display, read, correct, message, and process will be called. That's according to dynamic binding. Okay, so let me just write down one more thing. So this would be the context objects, which is really important for you to realize. Okay, so now let's go to the architecture for the state design pattern. Okay, so this is the design architecture for the state design pattern, which also consists of another sub-pattern called the template design pattern. So now, rather than showing to you the code or the implementation of the pattern, I would like to go over the architecture with you. So try to do the following exercise. As I go through every class and every routine that are critical for the communication of the pattern, imagine how you would actually implement it. So that might be a nice mental exercise for you. Okay, let me now switch to the illustration for the pattern, and then we'll talk about how to implement it from the supplier's point of view. Okay, so now let's talk about this. And I'll give you some illustration very quickly about dynamic binding and also polymorphism. Let's go over the design architecture over here. First of all, we start with some clients of the state design pattern. So you can think about this side over here is the clients. Okay, the client is simply just going to have a client-supplier relation over here, and then it simply got a states, which is effective. And then on the right hand side over here for the supplier side, we simply got the state class over here. And notice that this particular class is deferred, meaning that you cannot use the state class as a dynamic type, right? That's something we talked about before. So let me just highlight it over here. It can be a static type. However, dynamically, you just cannot choose the states. You have to choose one of its effective descendant classes. And also, let's take a look at the routines or features that will be available on the states. I would like to highlight so you can see read, display, correct, process, and message. Law of inversion, as we talked about in the previous video. So now, if I just remind you very quickly, display, read, correct, message, and process. All these routines have now been put into the data, the module of states over here. Right, so that's something I would like to draw your connection to. So that's exactly what the law of inversion really means from the previous part of the lecture. And notice that all these features over here are simply just deferred. Okay, notice that it's just part of the pattern over here. Think about all these routines are the important components for patternizing the state's behavior. Okay, so now you can think about all these will be used to define the pattern of interaction for the states. Let's write it down. So these are the components for defining the pattern or template. So this is why there's also the so-called template pattern that's actually consisted of in the state pattern. Template of states behavior. It will be supplied with concrete details a little bit later, but let's just talk about conceptual level. Okay, so these are the components. So what about the actual pattern itself? So as you can see, these are just the components, right? That's why I only say the components for defining. What about the actual component? That's the pattern definition. It will be this only effective feature over here. You can see the execute routine over here. That's the only routine that's actually effective in the state class. So that one is the pattern itself. Okay, we'll see exactly how. But let me just put it down over here. So now for the execute, okay, I'll put it here. For the execute, okay, so this will be the pattern. Pattern or templates of states behavior. Yeah, let me just emphasize one more just in case you're confused. Because somehow they sound similar, but they are not. Think about the execute over here is the pattern, which consists of somehow some way to organize components of the pattern, in which case we can somehow we have to organize the read, display, correct, process, and message in a particular way in the pattern. So that's why these are just components. For individual components, they're simply just deferred because they have to be made effective in each of the effective classes of the state. And then for the pattern over here, because the general pattern for the state behavior is reusable, right? We talked about it before. So since the state pattern is simply reusable, we can make it an effective template in the state class already. We don't need to repeat the definition for here, 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 and here. We don't have to. Once we define the template itself, it can simply just be inherited verbatim without being redefined to every child class over here, right? So that's the idea. Okay, so we'll get there into the precise detail. And let's now talk a little bit more. Okay, so now we want to speak about also the individual classes. That's why I also include this initial diagram about our state finite state machine. You can see we have an initial states over here. That's why we have an initial class over here. And also we got a flight inquiry state over here. That's why we also got a flight inquiry state descending class over here, and etc. Depending on how many states you actually got in your formulation of the interactive system. In that case, you have this many states classes over here as the effective descendants, right? Okay, so that's about it. All right, so and then anything else? I think that's about it. And also notice that there's a slight notational convenience I'm using over here. Let me just show you. Basically, every effective class over here are inheriting from a common parent class over here. So rather than simply just say inherits like that, right? That could actually make your diagram a little bit messy. So what I'm doing over here is I simply have an inheritance error over here from their cluster. You can see the state implementation cluster. If I actually put simply from the boundary of the cluster to a class, so that means every class in this particular cluster it inherits from this particular class. It's just a notational convenience that you may want to adopt for yourself as well. Okay, so that's about the architecture for the state design pattern. So let me now just go a little bit more into the code, and then we can see exactly how the template design pattern actually works at the runtime. Let me give you a little bit of preview what's going to happen here. Now that we know the state class itself is deferred, so let's say if you declare S to be of type states statically, right? Dynamically, we know that we can choose any of the descendant classes over here, any of them. For example, I simply choose sit inquiry over here, and also confirmation over here, right? We'll repeat the example in more details later. But now, if I try to do these two dynamic type initialization, right? Either I do this one here or I do this one here. So now, ask yourself the following question. If I try to say s.execute versus s.execute over here, are these two execution of the execute going to be going to exhibit the same behavior? Okay, so that's a question, right? Think about it very quickly. Okay, I can tell you right away they are not going to behave the same, because here the execute is going to behave with respect to the dynamic type, which is the sit inquiry. On the other hand, over here, the execute over here is going to behave with respect to the dynamic type at this point, which is confirmation, right? So that's something you would like to pay attention to. So that's a very quick informal sketch. And let's now talk about the code structure for the supplier side for the design pattern, for the state design pattern. Okay, let's go back to the slides. So first of all, let's talk about the states ADT, the class. So for the state class itself is deferred, as we said. And then we're going to make all the routines at level number 1 in the second design attempt. They're going to be state specific routines right now. You can see we got the read. The routine is simply just deferred. We got answer, simply just an attribute here. And then we got choice. Also, basically, think about answer and choice will be updated if the user try to give some answer or choice for that particular states. And then we got display, which is also deferred. We got correct, also deferred, and also process and message. So these are all the routines, all the helper routines that used to take the parameter current states in the second design attempt, but we don't do that anymore. You can see this particular routine, for example, is simply parameterless. There's simply no parameter. Used to be to say read and also taking the current states in the previous design attempt, right? Remember, I'm not going to show you. You can look it up yourself. Okay, so you can see all the features so far. Read, display, correct, process, and message. All these are simply deferred. They simply just correspond to what we set over here, right? Just to verify that. So now, finally, we're going to present this particular execute as I just previously informally described. So this is going to be the pattern for the state behavior, whereas all the defer features over here, they are simply the components for the pattern. So now, in the pattern itself, it's going to somehow organize the components of the pattern in a way that's going to be done by some control structure. Okay, so let's see how exactly it's going to be done. So now for the execute, we simply declare some local variable good to see if the user has supplied good inputs for the current states. And then we got some from until loop. We have seen this loop structure for many times already from the previous design attempt. So hopefully that's not really strange to you. So we are saying that as soon as the user's input and answer are actually good, so in that case, we're going to exit from this particular state. Otherwise, we have to keep prompting the user for good inputs. So we're gonna, first of all, you can see we are trying to patternize the components of the pattern, right? So now we call the display. Notice what we're doing. We say display. We're calling the display, which is deferred. We are calling the read, which is also deferred. And then we are also calling the correct, which is also deferred. And then we are calling the message, which is also deferred. We are saying that if the input from the user currently is not good, in that case, we have to give them some error message, and then we have to run the current iteration once more to repeat it until they actually give us the good input. So, and then finally, once we exit from this particular loop, so that means all the inputs are good. So we can now process. You can see process is also calling something that's deferred in the same class, right? So that's about the code structure here. Just get yourself familiar, and now I'm going to do some in-depth illustration to see what's happening over here. Okay, so now what we want to do is look at the structure over here, and then we're going to see both at the compiler time and also at the runtime. Number one, so here as I box this particular fragment of code, let me just box it again. You can see this part over here is the so-called template. Okay, this part over here, template or pattern. And then every routine that we actually refer to, every components of the pattern we're referring to over here, for example, display is really referring to the deferred display over here, right? And also the read is also referring to the read, also deferred over here. And also for the correct is also referring to the correct over here. And also for the message is also referring to the message over here. And finally, for the process is also referring to the process over here. And I really want to illustrate the following point. You can see every component that's being referred to, they're all deferred. Deferred, and also deferred. But they are being called in the context of a routine that is actually effective. So now it's really important to realize the execute feature over here or routine is actually implemented or effective. Effective or implemented. In order to implement something, you can actually refer to something in the blue that's actually not implemented. So that's the key of how things are going to work. And everything compiles, nothing's wrong. Okay? So now let's think about how things will work at the runtime. So now it will be very important. So the example I want to give is exactly what I wanted you to review previously. So let me just give you a simplified version of the inheritance hierarchy. Okay, let's recall the inheritance hierarchy. At the top level, we have the state class over here. Okay, this is our state class, and then under which we actually got two. We got actually 1, 2, 3, 4, 5, 6, 7. We got 7 different classes, right? So now let me just put 2 of them. I'm going to put sit inquiry versus over here another one called confirmation. I'm going to put these two, okay, just these two. So seat inquiry is a subclass of the states. Seat inquiry, it is deferred. And also I got another one, confirmation, which is also a subclass of the states. So that's the confirmation class. And notice that that's also effective. Let's be a little bit more careful over here about the routines. And remember, the execute is actually effective, right? That's exactly the execute over here. And now the one we want to, let's just take a 2 for example. And also here we got display. Let's say display and also read. So these are simply just deferred, right? I'm just basically copy and pasting from the architecture diagram. And now for this, for execute, it will simply just be inherited verbatim to state inquiry and also confirmation. But now for each one of them, they should define their own version of the display and read. For example, display should be effective over here, and also read should be effective. You can think about this is the version for seat inquiry. And also we're going to have display over here. And also we got read over here. And you can think about this is a different version of display and read just for confirmation. Okay, that's something we want to make sure you understand. So now let's talk about this. Now I say I declare S to be of type states. So S being static type is simply just states. And the runtime is going to store the address of some state objects. Let's see the very first one. The first one here we say creates seat inquiry s.make, assuming that make is a valid constructor. So now what this does is it's now going to let S pointing to a seat inquiry object over here, meaning that after this line here, dynamically S dynamic type will just be seat inquiry, right? Let's not worry about the attribute in the state class just yet. Okay, so now when you say s.execute over here, so now what's going to happen over here? That's really important. So now s.execute, you want to know according to dynamic binding, which version of execute to call depends on the dynamic type for S. So now what's the dynamic type for S? Well, dynamic type for S will just be seat inquiry. And now, which version of the execute are we going to call? Well, in this case, because we know that for the execute, it's simply inherited verbatim to both classes, both descending classes. So now we are really calling this particular version of the execute, right? Just a single version. That one's no problem. But now let's dive deeper into exactly how each line will be executed in the execute routine. So now, when we try to run this particular one, okay, the blue one over here, right? The blue one corresponds to when the dynamic type is simply seat inquiry. So now when we get to the display over here, so now when we call display, it will be as if the context object is simply just S, right? Since we say s.execute. So when we say s.display, and also when we get to this particular line over here, we're going to call s.read. So now the question is, which version of display and which version of read are we calling? Well, according to dynamic binding, we will know that since the dynamic type is actually seat inquiry, so we know that this execute over here is going to call the display. Let me just be more precise over here. We want to know the version of the routines that's being called. So we want to know the following. Okay. So now for s.execute, so now we're going to call first of all from the state class. From the state class, we're going to call that particular version of the execute, right? So once it is now done, it's going to call the different components in the pattern. When we call this particular display and we call this read, because dynamic type is simply seat inquiry, so now it's going to be seat inquiry dot display. And also this one here is going to call the seat inquiry version of the read. We didn't really show you how exactly you will implement these two, display and read, in this particular seat inquiry class, but you can assume that it has been done somehow. Okay, it's just important to notice that there's always one version of the execute, and then when you actually execute this pattern over here, this common pattern among all the states, you're going to call dynamically different version of the display depending on what the current state is. And similarly, you're going to call different versions of the read depending on what the current state is. Okay, that's really important to notice. So now let's continue with our argument over here. So let's say we try to execute this line over here. So when we say creates confirmation, so what we're doing is, as rather than pointing to the C inquiry, it is now going to point to another object dynamically. And now this time it's going to be confirmation. Okay? And now when we try to call exactly the same line, s.execute over here. So what's going to happen, right? That's also important to realize. What's going to happen is, first of all, which version of the execute are we going to call? Well, dynamic type is confirmation. And for confirmation, we know that this only is simply inheriting the execute from the states verbatim. So we know that we are calling the same execute routine once more. So now we know that it's going to call simply the same versions of the execute. So state.execute. And by the way, hopefully my notation here makes sense to you. So when I say curly brackets and state, I'm simply saying we're calling the execute from this particular class. That's what I meant, the version. So now we know that since we're calling the same pattern, so it's going to call different individual components from the pattern. So now, first of all, it's going to execute also this block of code again. So now when it hits display over here, it's going to say s.display. But now this time, s dynamically is actually pointing to a confirmation object. So that means we're going to, according to dynamic binding, we're going to call the confirmation version of display, which is over here, right? So now that means we're going to go for the confirmation version of the display when we hit that line. And similarly, when we hit this particular line for the read over here, when we call s.read, according to dynamic binding, since the dynamic type is actually confirmation, so that means now we're going to call the read this particular version from the confirmation. So now it's going to be from the confirmation class, we're going to call the read. Okay, hopefully you can see how exactly the template design pattern actually works. Let me recap very quickly before I move on. You want to really understand that for this defer class states over here, only the executed pattern itself is effective, whereas all the individual components of the pattern are deferred, number one. Number two, at the runtime, depending on what the dynamic type is for the states, you can see statically we try to be as general as possible. We don't say any, that's too general. We simply say states. And then dynamically it can be any of the effective descendant classes under the state class, meaning that it can be either this, or this. So now, whenever you're calling the pattern here by calling execute, because there's only a single version of execute over here, it's not redefined. It's not meant to be redefined in any of the descendant classes. So you're only calling this single version. However, when you're calling the individual components of the pattern, since you can see they're simply referring to the defer feature over here, right? For example, you can see the display here is simply referring to the defer over here. However, at the runtime, because of dynamic binding, it's going to make sure it call the display that's actually effected already in either this class over here or in this class over here. So depending on what the dynamic type is. So that's why in this version over here, it's going to call the display from C inquiry. But now in this particular case over here, since the dynamic type has been changed, so you're going to call the display from the confirmation class. So really try to understand exactly how the template and also state design patterns over here work from the supplier side before we move on to how the client is going to use the design pattern.